Welcome. I'm Grant Sewell, Senior Applications Specialist at Canadian Measurement-Metrology. And today I would like to take a little time to show you some of the key features of PC-DMIS 2011.
I'd just like to start by mentioning that PC-DMIS 2011 has full support for Windows 7, 32 or 64-bit environments. So if you're using any of those operating systems, you'll be ready to go. So I'd like to look at the user interface first. Let's just open up a PC-DMIS part program and get an overview of this interface. So on the left-hand side, we've got something called the Edit window, and this Edit window keeps track of our part program's commands. And there's several ways we can view the commands in the Edit window. Right now we're looking at something called Summary mode, and in Summary mode we get an overview of the commands that build up our part program. If we want to look at the details of any of these commands, we can expand the branches of the tree, and we can come in here to things like Settings, and I can just double click on this plane feature and I could type in a new name for it. Okay, so that's Summary mode. We also have the ability to view the Edit window in something called Command mode. And Command mode, you get more details of the part program's commands. And I just want to mention, you don't have to learn a programming language when you're programming in PC-DMIS. All the features that we measure or create are dialogue based. So that means, and I'll just put the cursor at the end of the part program here, if I go in and if I construct a feature, let's say a point, we have a dialog that appears, and let's just get a point at the center of one of our cylinders here. And I'll just hit Create and Close, and by doing that, that adds a command to our Edit window. You can see over on the left-hand side, and we'll just go back to Summary mode there, that we've got a point that was constructed, and that construction was based on our cylinder. So that is the Edit window on the left-hand side. Now, where you have your cursor inside that Edit window is going to affect where the next command is inserted. So if I've forgotten a command, it's really easy for me to go back through my part program and add whatever it is I've forgotten. I can just put my cursor there and then do another measurement or another construction, and the new command will end up in this spot here. For instance, let's go under Report command here and add a comment. We'll just add a comment to place the part in the holding fixture. When I select OK, that command is added where I've left my cursor. So very easy to make changes to your part program as well. Wherever your cursor is, that's where the next command is going to go. Now, our measured features, we can hide and show the labels for our measured features just by selecting this toggle feature label IDs. And we can see that all the features that I've created have a label now that's pointing to them. Another thing that's great about this Edit window, if I want to make a change to one of my features, I don't need to know where it is inside the Edit window. All I need to do is right mouse button click on the feature itself, a context menu appears, and I can select this, Edit. And what you're seeing is the dialog that was used to create this feature. And PC-DMIS has located cylinder 8 inside of the Edit window. It's opened up the dialog that was used to create cylinder 8. And if I just zoom in so that you can see, it displays on the screen the points that were used to create cylinder 8. And then I can do things like change the number of hits. Let's say we want to make 12 hits per level, and we can see my graphics update, and I'll select OK. PC-DMIS is going to animate that inspection if I wish, and it's going to update the command inside of my Edit window. So making changes to your part program, really easy. all the PC-DMIS dialogues also have a context-sensitive help screen that's associated with them. In order to display the help for any dialog that you're looking at, simply hit the F1 key on the keyboard. This looks up the appropriate help in the help system. On the left-hand side of the help screen, the Favorites tab allows you to add favorites so that you can quickly look up commands that you're having trouble with. To the right of the edit window, of course, we have the graphics display window. And this is the window that keeps track of our measurements graphically. And if we're working with a CAD model, it's also going to show us that CAD model. A couple of other things that you're able to do inside of this graphics window is we can insert and use fixtures inside of this graphic window to set our model on. So if I go under Insert, Hardware Definition, I've got a mode called Quick Fixture. And if we just have a look at what we have in here, we've got several manufacturers have given us their part numbers. For instance, R&R fixturing. We have all the components that R&R sells with their part numbers. And so here are all the base plates, and we can see if we select one of the part numbers, we can see a preview of the base plate right down here in the lower left side. Okay, we've got magnetic holders and standoffs and tension clamps. Okay, we also have the same thing for the Swift fixture kits, Taco kits, and you can even have user-defined fixtures. And what I've done is I've taken several of the R&R components and I've defined a fixture, and I call it the hex block fixture. And if I just insert that in my part program and select OK, we can see a fixture over here just above the part. Now, to get that fixture and the part matched up, I can go into a mode called Quick Fixture Mode. And I'm just going to turn off my labels for a second to do that. So I'm going to go into Quick Fixture Mode, and this allows me to drag my part so that it sits on top of the fixture. So I'm just going to drag the part on top of the fixture. And we can see the part's hidden behind the fixture. So let's just go to a different view, and then we can just move these features together. And we'll do a scale to fit here. We'll go to the top view and just fine-tune the placement of our fixture. There we go, something like that. And I'll just move it down a little bit in the Z direction. And now the reason why you'd want to do this is so that when we do something called a collision detection, we can account for the position of the clamps on our holding fixture. Now, the other thing that I can put inside the graphics display window is a representation of the machine. So if we go under Insert, Hardware Definition, we've got something called Machine. And we'll go in here, and there's a list of all the machines that Hexagon Metrology sells. And we'll look up our machine here that we have in our showroom, Global DIA 915-8, and you'll see a picture of it, and I'll just hit Apply and OK. And now we can see that we've got our machine and we've got our fixture off to one side. We'll fix that in just a moment, but we've got a picture of our machine in the graphics display window. Now, to get our fixture on top of our machine, we can just go back inside of Quick Fixture Mode, and we can just drag the whole assembly right down here. And we won't go all the way down in the Z there. We'll just drag it over in the approximate area, go to the top view here, kind of get it towards the front of our machine there, and we can zoom in a little bit and just set it right down there on the base plate. We jump out of Quick Fixture Mode, and now we've got our part and our fixture sitting on top of a representation of our machine. So now let's use our graphics display window to perform a collision detection. The first thing we need to do is enable path lines. So we're going to go under View and select Path Lines. And what PC-DMIS does is draws a representation of the probe path around the part, including all probe changes. What we'll do now is we'll go under Operation, Graphics Display Window, and select Collision Detection. PC-DMIS is now inspecting our part in a virtual manner and looking for any collisions between our part, the fixture, and our probe, and even our machine. At the end of the collision detection, a collision list is displayed, and any possible areas that might be a problem, if I select in the list, PC-DMIS will highlight in the path the region that could be troublesome. So we can see this region right here is awful close to the part. And it's actually not a collision, but it's within a tolerance that I've set up, and so it's counting that as a collision. So what I can do is I can just click on this path line right here, and I can input a new value. And PC-DMIS is going to update that path line, and in this method, I can fix any collisions that might occur in my part program. And we'll just select Apply, and then we can clear this list and select Cancel, and if we wanted to, we could run it again. If we wanted to have a little more control over the speed of our collision detection, inside the Setup options in PC-DMIS, you'll now find a new tab called Animation. And inside of that Animation tab is a slider. It goes from 100 to 1%, and we can simply just turn this down to a slower value and then perform our collision detection. And this is going to help us better perceive the performance of our part program. If you've used previous versions of PC-DMIS, you'll notice a change in our menu system. All pull-down menus now have been reorganized to be more logical and compliant with a Windows standard interface. On the left side of the Quick Start dialog, we see some icons to perform some commonly encountered tasks. For example, we've got Calibrate Probes. Underneath that, we've got Alignments. And because the Alignment dialog contains multiple types of alignment, a flyout appears showing us all those alignment types. The same thing is going to happen when we hover our cursor over Measure, Construct, or Dimension. Let's try out one of the canned routines for performing an alignment on a part. I'm going to hover my mouse over the Alignments dialog, and I'm going to select Plane, Line, Line. When I do that, PC-DMIS displays a dialog for measuring a plane. And inside of that dialog, we see that we're required to measure at least 3 hits. So I'm going to grab my probe and I'm going to measure 3 hits on my CAD model. If you were online on a CMM or a portable device, you could simply go over to your part and perform the measurements that way. Once I'm finished measuring the plane, PC-DMIS is now prompting us to measure a line. And again, we'll measure a line on our CAD model. By utilizing the CAD model in the inspection, PC-DMIS is able to extract the correct nominals for the features that I'm measuring. And finally, it's prompting me to measure another line. We'll do that on the left-hand side of the part. Let's have a look inside the edit window and see what this macro has completed for us. This is where the macro began, and it prompted us to measure a plane. And PC-DMIS automatically inserted an alignment command after the measurement of that plane. This alignment command levels the plane. Then we have the measurements for our two lines, and the macro routine now has constructed an intersection point between those two lines and finished off our alignment by rotating the first line and setting the origin at the intersection point. So that's an example of the Quick Start dialog and how it can be utilized to quickly build an alignment for your part program. Another area inside the graphics display window that people find useful is at the bottom here, called the status window. The status window can be toggled on and off as needed using an icon on this toolbar. And what this is going to do for us, if we measure a feature, and I'm just going to measure a diameter here, that status window is going to give us a preview into the results of any measured feature. You'll notice after the minimum number of hits is taken, we get a preview of the nominal, measured, and deviation for this feature. Of course, I'm programming offline, so the measured values are the same as the nominal values. Another new tool that PC-DMIS makes use of is the ability to utilize and read feature control frames that are attached to the CAD model. This icon right here allows me to see any of the feature control frames or tolerances that are embedded inside of this CAD model. CAD platforms such as CATIA and Unigraphics support this ability. Once I've displayed these feature control frames, I can program very quickly on the screen by going into CAD select mode. And if I select one of my datums, for instance, I'm going to rotate and select datum A, PC-DMIS is going to generate the code for measuring datum A and setting that as a datum feature. If I select one of the feature control frames that utilizes multiple datums, for instance this true position here, PC-DMIS has automatically added the code to measure those multiple datums, set those multiple datums up inside of our part program, and then we're now presented with an exact measure GD&T position dimensioning dialog with a compound callout for the feature control frame that I selected inside of our graphics display window. The only thing I need to do is put in some tolerancing for the size. This tolerancing for the size was obviously not included in the feature control frame. Let's grab one more thing, for example, a perpendicularity callout to datum A. You'll notice that the feature control frames that I previously selected and inspected are now switched to gray. This is your indication that you no longer need to inspect these features. So next I'd like to show you some of the controls we have over the CAD model inside the graphics display window. Many of the CAD packages out there support multiple coordinate systems attached to the CAD model. PC-DMIS supports that now through the use of an icon called Coordinate System. And if I select this icon, we can see I can choose any of the embedded coordinate systems to start my part program. We've got car position, and if I select Apply to car position, you notice that PC-DMIS has offset the part and put it into car position. If I select Local Coordinate System, we can see we now have a trihedron that represents a local coordinate system for the part. Of course, we're going to want to select these coordinate systems before we do any part programming, but we have this flexibility. In addition to the coordinate systems, PC-DMIS also supports CAD assemblies. So if we select Assembly and you're working with a CAD package like CATIA or Unigraphics or any of the other packages that support assemblies, all the parts that are in your assembly will be listed on the left-hand side of this CAD assembly window. And I've just gone ahead and built a simple assembly here with just two of the test blocks, and I've labeled them part 1 and part 2, but you'll notice that I can just turn them on and off at any time. And so if you bring in an assembly, you can turn off some of the fasteners in the assembly or enable the smaller components in the assembly to facilitate CAD programming. Now, in addition to assemblies and coordinate systems, PC-DMIS also supports CAD levels that can come in from different CAD packages. On our toolbar again, we've got an icon here for CAD levels, and you'll notice I have 4 different levels on the go here. And for instance, if I just turn off the first 2 levels, you'll notice that the remaining levels only show the wireframe for one of the parts and the logo for the other parts. So this CAD level information can come in directly from your CAD package, or there's the facility in here for creating new CAD levels and assigning geometry from your CAD model to a CAD level of your choice. And you can have as many of these levels as you like. The latest version of PC-DMIS 2012 has implemented something called Part Program Archives. And this is a handy thing. What it's going to do for you is automatically back up your part program when you do 2 different operations. The first time it's going to automatically back up your part program is when you save a part program. So when you save a part program, PC-DMIS is going to create this file, PRG tilde, right here. In addition to that, it's going to actually perform a save, of course, with this extension, .prg. And you're free to rename these and go back and use them at any time. The next operation where PC-DMIS will automatically archive your part program is before loading up a part program. And this is handy if you know that you're going to make changes to the part program, but you still want a copy of the original. As soon as you load the part program, before you load it in fact, PC-DMIS will make a copy of it with this extension, .prg up arrow. And of course, then it's going to open the PRG file and run as normal. So we get some redundancy in our part program and auto archiving. That's a real benefit. We've had a little look at the user interface in PC-DMIS. Let's dig a little deeper and look at the details by creating a part program offline. We'll go File, New, and under the interface, because I'm offline, the only option I have is offline, of course. If you're attached to a CMM or an ARM, you can choose interface offline or the device, which is the machine. We'll give it a name, Offline Program Test. And on the right side, we can choose the units, inches or millimeters, and we'll select OK. The first dialog that appears when we build our part program, whether we're online or offline, is the Probe Utilities dialog. And this is where we tell PC-DMIS what hardware we have attached to the end of our ZRAM. And I've got a probe file called testprobe1 that's been pre-configured, but you can build any custom hardware and give it any name that you like. For now, I'm going to select OK. The next thing that I'm going to do is I'm going to import a CAD model. Now, a little bit about importing CAD models. We can translate CAD models using any of these formats that you see on the screen here. ASCII file, CAD, CATIA 4, CATIA 5, DES, DXF, IGES, JT, Parasolid. We can bring in a point cloud of various formats. We can use ProEngineer, STEP, STL, Unigraphics, VDA, XML, and XYZ. Now these are known as translated formats. We also have the ability to use something called a direct CAD interface. And the direct CAD interface, the way that it works is it will talk directly to your CAD package. For example, we've got CATIA 5 here. We need a seat of CATIA 5 on the workstation that you're using to run PC-DMIS. PC-DMIS then would talk directly to CATIA 5 and get the CAD information directly from CATIA 5's CAD engine without translation. We can do the same thing for CATIA 4, Ideas, Pro Engineer, SolidWorks, and Unigraphics. Remember, this direct CAD interface requires that you have the CAD package that you're speaking to installed on the PC-DMIS workstation. For now, we're just going to import an IGES file. And I'm just going to grab the IGES file for the hex block test part. So we can see our test part on the screen. We can make use of this IGES file in a number of different ways. I'm going to go into what's called program mode, and in program mode a representation of the probe appears on the screen, and I can simply touch on the CAD model to generate hits. I don't even need to tell PC-DMIS what I'm measuring. PC-DMIS has something called automatic feature recognition, and when I'm done taking the hits, I'll hit the end key on the keyboard, and PC-DMIS has recognized that feature as a plane. I can do the same sort of thing on the front of my part to measure a line. I'll hit the end key again. PC-DMIS recognizes those two hits as a line. I'll zoom in to the left side of our part and I'll measure a small line on this lower left corner. You'll notice that PC-DMIS draws the vectors for the individual points of my line. I'll now use the toolbar called Constructed Features to build an intersection point between those two lines. PC-DMIS has a mode in the construction dialogues called Auto. In Auto mode, PC-DMIS tries to guess the sort of construction that require two lines as an input. And we can see in the edit window on the left-hand side that PC-DMIS has constructed an intersection point from those two lines. Let's now build an alignment from this data. To satisfy the requirements for an alignment in PC-DMIS, there's three areas we need to address. This area over here labeled Level, an area below it labeled Rotate, and an area below that labeled Origin. So I'm simply going to grab my plane and I'm going to select the Level button. That levels my plane. I'm going to grab my first measured line and I'm going to select the Rotate button. That takes my coordinate system and rotates that line to the X plus axes in my coordinate system. I need now just set some origins. I'm going to grab our plane and I'm going to set the Z origin on the plane. I'm now going to take our intersection point and set our X and Y origins on the intersection point. We select OK. Inside of our edit window, we've now built an alignment. We can now switch our part program to automatic inspection. We'd use this toolbar here labeled Probe Mode, and we're going to select DCC mode to switch our part program into automatic. Again, inside the edit window, we have a command manual/DCC mode. At this point in our program, it would probably be a good idea to inform the operator that we're going to jump into automatic mode. To do that, we can insert a comment into our part program. One of the new features of PC-DMIS is the ability to import media to add to our comment. The media that's supported is bitmaps, PNG, JPEG, and AVI files. I'm going to select this bitmap file, and I'm going to type in some text, drive clear, and prepare for DCC. We'll select OK. We should now think about inserting a safety move at the beginning of our part program. If you look at the bottom of the screen, you'll notice a digital readout window. And if I click on this digital readout window, that's a shortcut to bringing the move point dialog to the foreground. And I have several options in here. I can type in a value to move. I can move offset from a CAD surface. I can move offset from a feature. What I'm going to do is I'm going to build an offset from a clicked CAD surface. And the way I do that is just by selecting the CAD surface, and you'll notice that PC-DMIS fills in the XYZ coordinates based on where I've clicked and that offset value of 150 millimeters. If I select Create, I've now added that offset to my part program. The other means that I can control movement in the part program is by going into program mode and right mouse button clicking inside of my graphics window. Wherever I click the cursor, the probe follows the click. I can simply use the Control M key on the keyboard to record that move point in my part program. I can also go under Insert, Move, and select Move Point. What PC-DMIS does is it reads the graphical position of our probe on the screen and inserts that as a move in our part program. Another option for controlling motion in our part program is to set up something called a clearance plane. We'll just select an icon here for clearance planes. And basically a clearance plane is just a safety zone around the part. And we can set them up in one axis at a time. I'm going to set up a safety plane around the Z plus axis. And I'm going to tell the software before it measures any feature, it must move to 30 millimeters in the Z plus direction. And now when I measure a feature, PC-DMIS is going to insert a Move to Clearance Plane command before the actual measurement. And it will do that for each feature that I insert in my part program. A dialog that offers us more control over the creation of our features is this dialog right here, Auto Features dialog. And if I select the first entry in this toolbar, called Vector Point, rather than just click on the screen, we're presented with an interactive dialog. For the vector point, this dialog will present the surface normal vectors in the region where we select our point. I'll select a point on the side of this cone, and you'll notice that if we zoom in a little bit, we have a vector that represents the surface normal for this point. Inside the Auto Features dialog itself, on the right-hand side, we see the I, J, K representation of that vector. These I, J, K values ensure that PC-DMIS calculates the probe compensation correctly, which is always done along the I, J, K values. In addition to displaying the I, J, K values, I can do things like attach an avoidance move to this feature. This particular avoidance move is set at a distance of 10 millimeters, and it'll occur both before and after the measurement of this vector point. The Auto Features dialog also contains provisions for measuring other geometric primitives. Let's have a closer look. If we select the pull-down on the upper left-hand side of the dialog, you can see we have not only vector point, but surface point, edge point, angle point, corner point, high point, line, plane, circle, ellipse, round and square slots, notches, polygons, cylinders, cones, and spheres. Let's go ahead and measure some cylinders. When I click with the left mouse button on the inside of any of our CAD cylinders, PC-DMIS is going to extract the nominal, vector, and size information for that particular cylinder. PC-DMIS also extracts the length of that cylinder. What we need to do is constrain our measuring depth to accommodate the probe that we're using. We can do that on the Contact Path Properties page of our Auto Features cylinder. In this page, we have the number of hits per level, the initial depth, the ending offset, and the number of levels. Let's go ahead and adjust the ending offset to something like 20 millimeters. When we update that, you'll notice that PC-DMIS constrains the points inside of that cylinder to a depth from the bottom of 20 millimeters. We'll hit Create on this feature and add it to our part program. While we're at it, we'll select some more cylinders to add to our part program. Once you've set up the parameters for the first cylinder, the remaining cylinders will use the same parameters. In this particular cylinder, the parameters of minus 20 mils as the ending offset are not appropriate for the length of this cylinder. So we can go back under Contact Path Properties and adjust this to a value that is more appropriate. Let's increase the number of hits per level for this cylinder as well to 16 hits. If we zoom in, you'll notice that the software wants to take a hit in an area that is containing a void. We can enable a feature inside of PC-DMIS to avoid placing hits inside of a voided area. This is called void detection. And as soon as I select this, PC-DMIS adjusts our points so none of them fall inside of the void. Of course, PC-DMIS can measure external features as well. Let's select the Auto Features cone icon and place some points around the periphery of this cone. Single click should do it. We'll hit Create. Let's measure some diameters next. We'll select Auto Features Circle and we'll click in this diameter, and we have, it looks like 4 points inside of this diameter. So let's adjust this to 12 points. And you'll notice that some of the points PC-DMIS has color-coded. The orange point represents the ending angle inside of the dialog. The red point represents the starting angle inside the dialog. Any of these points can be dragged. So on the screen, I can manually adjust the position of my start angle and my end angle. If I wish to adjust any of the points in between the starting and ending angle, I can simply drag those as well. This makes it really convenient to place the points where you need them. We'll hit Create on this feature also. Another useful tool inside the Auto Features dialog box is something called Auto Wrist Toggle. And if I enable this, PC-DMIS will look at the vector of the feature that you're measuring, and it will calculate the probe angle that is required to measure that feature. It will do this automatically. You'll notice inside of my edit window, PC-DMIS has calculated it needs a probe angle of A90 B minus 22.5 degrees to measure cylinder 5. This functionality can be turned off and on at any time just by selecting the auto wrist icon. Placing points on very thin sheet metal trim edges is easy to do in PC-DMIS as well. We'll just use our auto edge point command and we'll select an area that we wish to place this point on. In order for this to work, especially with very thin sheet metal parts, we're going to enable something called sample hits. There's a useful tab inside of our edge point dialog labeled Contact Sample Hit Properties. This is where we can enable our sample hits and some other parameters that control the motion for these sample hits. I'm going to go ahead and test this out on the screen to see if the parameters I have typed in here will work correctly. The test button will allow me to test out these parameters. You'll notice the probe comes in and measures a small plane at the top of our trim edge. And then it goes down a specified depth and calculates the trim vector. Finally, it comes in and takes a hit, and that is our edge point projected up to that surface that we first sampled. The Auto Features Notch function inside of PC-DMIS allows us to measure a square slot with one side missing. Inside the dialog, there's a button labeled Move To. If we're programming on a CMM, this Move To button will allow us to move the probe over top of the feature. Let's go ahead and create this notch feature. Anyone using an analog probe such as the SP25 or SP600 will appreciate the ability to automatically scan inside of any of the auto features. All we need to do is change the probing strategy. We can select Circle Analog Scan Strategy right inside the Auto Features Circle dialog. This dialog allows me to apply point density, scan speed, and any filter outline that I wish to use with this particular scan. A dedicated scanning dialog allows us to collect points in areas of the part that contains complex geometry. If we select Insert, Scan, we have a number of different types of scans: linear open, linear closed, patch, perimeter, section, rotary, UV, freeform, grid, section cut, and the scans at the bottom, circle, cylinder, axes, center, and line, are dedicated to analog probes. Let's go ahead and put a linear open scan on the top of this part. First thing we need to do is select the CAD surface or surfaces that we wish to use to control our scan. Next thing we'll do is place some boundary points on those CAD surfaces. The parameter over here called Direction 1 Technique allows us to specify the increment between scan points. Path definition allows us to generate these points even though we don't have a real part. You'll notice the points are 3 mils apart. The nominal values reflect the nominals of the particular CAD model. The linear open scan allows us to scan in a straight line along any direction we choose. Let's change this over to patch scan. A patch scan is going to be a scan that's actually a 3D segment that we can bound with points. Let's go ahead and do that. We'll place a start point, a direction point, and these remaining boundary points constrain where the patch will occur. Under our Direction 1 technique, we also have something called Direction 2 technique, and this is going to constrain the step-over distance between our individual scans. Let's go ahead and generate these points as well. You'll notice a nice distributed grid of points on the surface that we selected. The perimeter scan allows us to select a surface and place points around the perimeter of that selected surface. Let's go ahead and try that one out. I'm going to select this top surface, which has a number of trimmed entities. And I'm going to tell the software to calculate some offset points from those trim entities, a distance of 1 millimeter. Our bounding points in this case are going to tell the software the region to use along our perimeter. If I select Calculate Boundary and then Generate Hits, you'll notice that now we have points 1 millimeter away from the perimeter of this selected surface. The grid scan function allows us to use the mouse to define a dense region of points. All we need do is drag out a rectangle. And over in the dialog, we can specify the point density that we wish to use. Now that we have a number of features added to our part program, let's look at some of the tools for optimizing the inspection path. If we select Edit, Optimize Path, and we say All Features, what PC-DMIS is going to do is it's going to reorganize the order in which it inspects these features to give us the shortest path. I'm going to go ahead and select OK. PC-DMIS has calculated a path length that is 38% shorter than it was previously. If I'm OK with that, I can click OK again, and in the Edit window, PC-DMIS reorganizes all my measured features to use this newly optimized path. Another option in the Optimized Path dialog is the ability for PC-DMIS to calculate tip angles for all the measured features. We have two choices here: only defined tips or all possible tips. Another dialog, Operation Graphics Display Window, Clearance Moves, Auto Insert Moves, allows you to automatically insert the moves for all your features after the creation of your part program. So this would negate any auto clearance moves that we set up by selecting Delete Existing Moves inside the dialog. I'm going to go ahead and select OK here. After PC-DMIS calculates the moves for all of our features, it displays the path lines on the screen. We could now perform a collision detection on these newly calculated moves. A big part of any inspection is constructing features that we're not able to measure directly. Have a look in our graphics display window. I need to calculate where the axis of cylinder 5 pierces this diameter, circle 3. To do that, I'm going to use PC-DMIS Constructed Features dialog. I'm going to select Construct Point, and the construction type I wish to use is called a pierce point. I'm going to grab cylinder 5 and the circle 3, and I'm going to hit Create. PC-DMIS now calculates the pierce point between cylinder 5 and circle 3 and displays it on the screen as point number 5. Now let's use the construction dialog to build a diameter somewheres along cone 1. To do this, we'll select Construct Circle, we'll pick on cone 1, and we'll change the type to From Cone. And there's two things we can do here. We can specify a fixed diameter, and PC-DMIS will tell us where that diameter occurs along cone 1, or we can specify a height, and PC-DMIS will tell us what size diameter occurs at the height that we specify. Let's input a height value of 10 millimeters. As our reference point, we're going to use the origin. As our reference direction, we're going to use the Z plus axis. When I hit Create, PC-DMIS builds circle number 4 at a height of 10 millimeters from our current origin. Let's look now at the dimensioning toolbar. Inside PC-DMIS, we support ASME Y14.5-2009. We also support the ISO standard 1101 and ISO 8015. All we need do is select it inside of the dimensioning dialog. I've just selected the feature control frame builder for building a true position. On the right hand side of this feature control frame builder, we've got the GD&T standard. And you'll notice the standards I've mentioned previously are listed in here. In order to dimension a true position for any feature, we first need to define some datums. There's a shortcut inside of the feature control frame editor for defining datums. It's labeled datum definitions. If we open up this shortcut, we can now take any of our measured features separate from the alignment we built earlier. We can select features to define datums. Let's grab plane 1 as our datum A. We're going to grab our intersection point between line 1 and 2 as datum B. We'll grab line 1 as datum C. As we define these datums, we have new commands that are added inside of the edit window. In addition, inside the feature control frame editor, our datums are now listed. Now if we choose one of our cylinders to calculate the true position of, we will have access to these defined datums. Let's input a true position tolerance of 0.5 of a millimeter. Material condition is also supported inside the feature control frame editor. We have three options: S, which is regardless of feature size; M, maximum material condition; L, least material condition. If the datums that we've decided upon are features of size, we will also have the material condition modifier for those datums as well. Let's add a size tolerance so that PC-DMIS can calculate the maximum material condition for cylinder 1. I'm going to hit Create, and PC-DMIS has now added that true position to our part program. Let's look at calculating the true position of multiple features at the same time. This is known as simultaneous evaluation of features. And to implement it, we can just bring up the feature control frame editor and we can select more than a single feature. I'm going to select in the graphics window cylinders 1, 2, 3, and 8. The datum structure that I'm going to use is going to be datum A as the primary datum, datum D as the secondary datum, and datum C as the tertiary datum. The reason why I've chosen datum D is because it's a feature of size, so we can apply a material condition modifier to it, and we can fix its maximum material condition at a size of 43.8 millimeters, which is directly from my drawing. You'll notice at the top of the feature control frame editor, we have 4 diameters at a nominal size of 15 mils, plus or minus 150 microns. And I'm going to select the Create button at the bottom of our dialog. This has added some information to our report window. If we select this icon on our toolbar, we can quickly display the contents of our report window. At the top of our report is the true position evaluation of a single feature. You'll notice the software is going to evaluate the size first so that it can calculate any bonus that is allowed. Underneath the size evaluation, the true position is called out and evaluated. Having the true position alone would not be enough to correct the part if there was an error. So underneath of the true position evaluation, we also have a position evaluation. Below that is the simultaneous evaluation of our 4 cylinders. So once again, the size is evaluated for each of the 4 cylinders so the software can calculate any allowed bonus. Then the true position is calculated for each of the cylinders. That true position is calculated based on the datum structure we provided, A, D, and C. The ASME spec allows wiggle room in our evaluation because datum D contains a maximum material condition modifier. So below that, we have a region known as datum shift that would document any wiggle room that this true position is allowed to use. And of course, below that, we have the X, Y, and Z position of each of our features. When using a datum structure that's different than our current coordinate system, PC-DMIS illustrates that datum structure with the use of a secondary trihedron. You'll notice on our graphics screen we have two trihedrons. The trihedron on the left represents the coordinate system that was built with our alignment. The trihedron at the center of this main bore represents the coordinate system that was used to evaluate the true position of our cylinders to datums A, C, and D. In addition to simultaneous feature evaluation, PC-DMIS also lets us employ compound feature evaluation. Here, we're looking at the true position of 4 cylinders that are 15 mils in diameter. And we're looking at them in two ways. The first callout looks at the true position of those cylinders fully constrained to A, D, and C. The second callout looks at this cylinder only constrained to datum A. This would control the perpendicularity of the cylinder to datum A. This is known as a compound feature callout. We can also switch over to composite feature callout, which changes the feature control frame slightly. You would use whatever is designated on your drawing. Both the flatness and the straightness callouts in PC-DMIS have provisions to allow you to specify flatness per unit. Here's an example of where I'm dimensioning datum plane A. The total flatness of datum plane A must fall within 100 microns, but a sub-area of datum frame A must fall within 50 microns. And that sub-area is divided up into 10 millimeter by 10 millimeter squares. Of course, we can do more than just true positions and flatnesses inside of PC-DMIS. The Dimension toolbar has facilities for performing all manner of dimensioning, including locations, distances, angles, concentricity, coaxiality, circularity, cylindricity, straightness, flatness, perpendicularity, parallelism, total runout, circular runout, surface profile, profile of a line, angularity, and symmetry. Let's try a few more of these. Let's select the distance dimension, and we'll simply get the distance between two of our cylinders. And in this case, I only want the distance in the X direction. So in the dialog, I can place a tolerance. The nominal value, because we've used the CAD model, is extracted directly from that CAD model. We'll select Create here, and we'll click on Close to close the dialog. Let's do one more callout. We'll get the parallelism between plane 2 and datum plane A. Anytime you select a dimension that is a GD&T based dimension, PC-DMIS is going to display the feature control frame editor to allow you to specify the datums that are required to constrain or inspect this feature. I'll select plane 2 on our screen, and we'll change our datum to datum A. We'll change our tolerance to 150 microns. And at the bottom of the feature control frame editor, we'll select the Create button. Now that we've dimensioned some features, let's look at the reporting options available to us in PC-DMIS. I'm going to select the Report window, and the first report type that we see is known as a PPAP report, Production Part Approval Process. In this report type, the nominals are listed on the left-hand side, along with 2 columns for the tolerance, the measured value, and then a check mark or a do not enter sign depending on whether the feature is OK or rejected. PC-DMIS employs a template-based reporting system, so if we wish to switch over to a different report type, we need only select a matching icon on the PC-DMIS toolbar. I'm going to select the text-only report, and you'll see that PC-DMIS has reformatted our report information automatically, showing us only text for our dimension features. The other report types that are available are CAD-only landscape. In this report type, PC-DMIS displays a picture of the CAD model along with the results in a label. These are live, so I can double-click and rotate and translate my CAD model or zoom in and zoom out as appropriate. The labels are also live, so I can place them wherever I wish. PC-DMIS by default will use saved views in our part program to display the CAD model and the labels. The text and CAD report style shows us both a graphic and the results right underneath of it. A built-in report template editor allows any of the report templates to be customized to suit the user's needs. Once we've chosen the report template that we wish to use, we can now decide on an output path. We'll select File, Printing, Report Window, Print Setup. We have several options. We can output the data to a file using either Microsoft Rich Text Format or Adobe's Portable Document Format. We can output to a printer. We could also output in DMIS format. In addition to outputting our report in those mentioned formats, we can also select File, Export, and we can select Output in Microsoft Excel format. This selection displays a dialog that allows us to configure what the output is going to look like. If we wish, we can also output the graphics of our inspection. If we select File, Export one more time, we can export our measured data in IGES, point cloud format, STEP, XML, XYZ, and some other formats. This allows us to get a head start in tasks like reverse engineering. We can bring in the IGES data into our CAD package and use that as a basis to build a model of the part that we've just inspected.